and his talks about defect-induced magnetism in a two-dimensional material.
Okay, thank you. So good morning, everybody. I'm Ahmet Avsar. I'm an EPFL fellow, co-funded by Marie Curie Fellowship. I'm working with Andras Kiss at Switzerland. And before starting my talk, I would like to also thank the organization committee for inviting the talk. And it was very helpful, and I learned a lot from the tutorials and also the regular talks. And it's also great to see that now the graphene TMDC has become quite advanced and the understanding is pretty well. And I will be talking about the magnetism. Yesterday Oleg already gave some introduction. So I will be talking about that part first, about the metallic magnets that we see, which is originated from the defects. And then later on, I will be also showing you some unpublished results, which are coming from the semiconductor. So platinum cyanide is quite interesting material. It has a thickness-dependent band structure. So whenever you go like below 3-4 layers, it turns into the semiconductor, and once it's thick, it's metal. So indeed, it gives you so much excitement in terms of like using as a ferromagnetic injector or using for proximity studies. And finally, I will give some outlook. Yeah, Roland already gave quite a nice introduction, so I'm going to skip. But once you go down, and because of the geometric anisotropy, you have the completely different interlayer and intralayer anisotropy, so which gives you like different alignment of the spin. So here in this review article, they already summarize the materials which have been discovered. And because of that, indeed, like it has been one of the most exciting topic in the research of 2D materials, last 2 years maybe. And many exciting results have come out. And maybe the most famous is the chromium iodide, which has the completely layer-dependent magnetism. Again, Roland, he introduced this very well. I will just tell very briefly. In the odd numbers, you have the ferromagnetic ground state ordering. And once you have the even, until the coercive field, you have zero net polarization. And then later on, the layers are completely aligned. And it's a kind of like an Ising magnet. All the spins are oriented out of plane. And these results were also confirmed by this single spin microscopy by a group in Basel and collaboration with Morpurgo. And basically what they saw is like all even multi-layers, they have like zero magnetization. And in the odd layers, 1, 3, 5 layers, they have roughly around 16 Bohr magnetron per nanometer square. And so this is quite interesting because now you have a chance to have a material system which is layer-dependent magnetic. And since it's also ultra thin, basically this means that you can also modulate the magnetism with the electric field. There have been like very nice TMR measurements. Indeed, by using even like some multi-layers, people have demonstrated that you can get like up to 1,000,000%, which is quite exciting. Maybe it's still like in terms of the critical temperature, it's not room temperature yet, but I think as a conception, it's quite interesting. And the second thing was they also demonstrated that by applying the electric field, you can modulate the coercive field, the transition from ferromagnet to anti-ferromagnet to ferromagnet by just applying the electric field, which is, I think, the key property in terms of the being 2D. And maybe Roland missed this part. There are so many bottlenecks with this material system. So this almost like all these 2D magnets which have been like shown to you until now, they are extremely degrading. So I mean, for instance, like black phosphorus has very bad reputation in terms of degradation, but based on my experience, you cannot even compare with chromium iodide. It's very crazy. Like you do, I mean, even degrade in the glove box, even if you encapsulate. So the main pathway for the degradation is like the substitution of the iodine by the water because of the photocatalyst effect. So basically, even if you encapsulate with HBN, within like half an hour, it has a problem. The second problem is it's also like quite resistive. So basically, if you want to integrate with the spin devices, it kind of like causes some doubt because it has a stability problem and it's also very resistive. I do feel that also like for spin torque related studies, it could be a bit disadvantage. But all these 2D magnets, they are intrinsic magnets, but you can also induce the magnetism with the extrinsic methods. So it was already shown yesterday by Paulo, and also today Roland was talking about. Basically, you can do the proximity-induced magnetism by placing a non-magnetic material on top of the ferromagnetic material. And the other method that the people have been studying is like doping with the 3D atoms. So for instance, the calculations were showing that indeed the manganese could be quite nice for TMDCs, but there is already a report from last year which was showing that if you do vanadium dopant to the tungsten diselenite, even with the concentration of the 0.1%, you can get you can observe the magnetism of the room temperature. And the third method, which have been like investigated mostly by the theoretical studies, but experimentally there was not so much. And I was interested in this like almost last 2 years. So, for instance, like people were predicting that theoretically the grain boundaries or strain, they could induce some magnetism. And in addition to these kind of the defects, we have also like vacancies, antisides, and also the substitution, which were predicted that indeed by themselves or with the combination of the both effects, for instance, like strain plus the vacancy, you can induce the magnetism. The problem was like these vacancies mostly related with the metal vacancies. So selenium or sulfur vacancies, they don't do anything in terms of the magnetism. But the problem is that the formation energies to create a metal vacancy is much more difficult compared to the sulfur. So the energies were quite high. And then there was a paper came out on arXiv which got my attention. It was like basically they were saying that creating the platinum vacancy, even though it's a metal, it can be quite small. So that was the idea, and then we were considering if these platinum vacancies would induce any magnetism. And there was a paper from Singapore, a group in Singapore. So basically they were doing the first principle calculations, and they were saying that they were showing that both the electronic structure and also density of states is spin polarized if you have the platinum vacancies in this material system, that they were predicting around 6 Bohr magneton. It was quite interesting, but it was for one layer. And this platinum cyanide, we were doing some charge transport before. And the problem is like getting monolayer is extremely difficult. So we were wondering if the multilayer would be also giving some kind of defects in this magnetism. And we collaborated with the Oleg, and his group was calculating for 6 layers of the platinum selenide. Basically, if the platinum vacancies in this structure, it would give any magnetism. Based on their calculation, what they were observing is if these vacancies are on the surface, yes, they contribute into magnetism, and this magnetism decreases as you increase the thickness, but it's magnetically dead if it's in between the layers, if it's not on the surface. And just very simple picture, if this is the case, if you have like a material which is like conducting, and basically just the vacancies on the surface, they are inducing the magnetism, then you can consider about these magnetic impurities which are mediated by the conduction electrons with the method like IKKY interaction. So here, how the coupling change on the distance, and then we got this Fermi wave vector from the RPS measurements from another group, and here, and then if you just put it, what we were seeing is indeed, this is very, very simple picture, but what we were seeing is indeed like you should change the sign, and almost with the one layer. So the periodicity was almost 2 layer, and basically one could also maybe imagine that you would have layer-dependent magnetism if it's just the platinum vacancies which are coming from the surface. And another question was, of course, like the calculations were predicting that, okay, you will have more easily to these platinum vacancies compared to molybdenum or tungsten in MOS or tungsten diselenite. But the question was if they really exist. So there was a STM paper which was looking for the CVT grown, which is the same method that we are using. Platinum selenide, if they have any kind of defects, basically they were showing that they have all sorts of the defects, and the defect density was in the order of 0.5%. We also did some TM investigations. So these were my first attempts. So I'm quite bad in terms of putting the crystals on top of the TM grids with very clean surfaces. So basically, I cannot get really a statistic, but I could already show that we have we have also defects on in the crystals that we are also investigating. So before I move to the magnet transport measurements, let me show you very briefly. So platinum cyanide is an interesting material. It's like compared to the other intrinsic magnets, it's very stable. And here you can see that after 1 year, nothing happens to the crystals. And as I told you, and yesterday Oleg was showing the DFT calculations, basically below 3 layer, you have the semiconducting behavior, and above is half metal, like it's basically like metal. And the third property is indeed it has an extremely low contact resistance, which could be indeed quite useful if you want to consider this material as a the spin injector. And so there are different ways of measuring this magnetism. So people use skewed, Mach, or anomalous Hall effect. Or crystals that we investigated, they were just ribbon. And indeed, we carry out the longitudinal measurements. So basically, this is the response you would expect if there is a ferromagnetic ground state ordering or anti-ferromagnetic ground state ordering. And there are some literature already which are directly comparing this system. And in the first part of the talk, I will be focusing on the magnetic samples. So basically, this is one of the samples that we characterize. So in order to not to have any spurious effects, we just use the non-magnetic contacts, and we have only, it's very simple structure. You have the platinum cyanide, which is contacted by palladium. We also try with the gold, so results are same. So, and then if you just look at the basic charge transport characterization, you will see that at this thickness range, it's quite metallic. And we got quite surprising results. So this is the response that we got from the first, like not the first, but 5 out of the 11 devices that we studied. So basically, once you scan the magnetic field out of plane direction from left to right or right to left, you see the this hysteresis curve, and we also saw some minor hysteresis curves by stopping here and then going back. So which is like kind of the indication of the ferromagnetic ground state ordering. And the delta arc is quite large. It's like 30 ohm. Indeed, at the low biases, it goes up to 400 ohm, which is like around 6% of MR. And if you do the temperature dependency of this, you see that it's there until 13 Kelvin. And above 13 Kelvin, you can see from the black one that the signal completely disappears. Indeed, if you also measure the charge transport in the device, you would also see that there is a indication that substitution of the spin-dependent scattering, which people have reported from such temperature-dependent measurements before. And once we moved to the other set of the devices, the transport response was completely different. So basically, this is the response we were getting. The other 6 devices, basically. So you have like this 2 plateau system, which looks very similar to what people were reporting with the bilayer chromium triiodide, which is like which has anti-ferromagnetic ground state ordering. So basically, we have very small hysteresis, but we have like these 2 plateau systems, which we believe that after here, the all layers are completely spin polarized out of plane, like this direction or that direction. And it's also a bit depending on the bias, and for this device, the signal was disappearing around 5 Kelvin. So if we put all the samples which have been like measured at the same bias, what we were observing is indeed here you can see that the red ones are the anti-ferromagnetic bands and the blacks are the ferromagnetic. You could see that kind of like there is an indication that it changes with the layer, which was very similar to this very basic prediction that we had previously. And all the samples which we have studied above 20 nanometer, they just show the weak anti-localization effect without any signature of the magnetic ordering. So we wanted to now investigate if there is a layer-dependent magnetism. So the natural way to look is like get a monolayer and then bilayer and then just compare the magnet transport properties. But as I told you before, that it's very difficult because getting monolayer and bilayer is difficult, and also they are semiconductor extremely resistive. So it's very difficult. So what we did is like, so this is the picture we had before, and basically we work hard to find like two crystals next to each other, and which are just like one layer different. So you can already see like these two crystals which are fabricated under the identical conditions, and which have only like a height difference of one layer, and we could already see that each of them show like completely different characteristics. Indeed, we have like more results, but I'm not going to show, but you can find in the paper by putting like some extra single layer fragments, and you will see that it indicates that layer-dependent magnetism. And I told you that the crystal looks quite air-stable. Nothing happens based on the Raman and AFM. Here, for instance, this is as exfoliated. This is after 3 months. I mean, we kept in glove box, but it was like after 3 months. And then we took the sample out and we annihilated 250. So you can see that there is no degradation on the material. And if you measure the sample like before and after annealing at 200 degrees Fahrenheit or 2 or 250 degrees of the annealing, we were getting identical magneto response, magnet transport response, which suggests that the magnetism is quite stable in this structure. And we also tried to minimize we also tried our best to prove that there are no foreign atoms which could also cause the magnetism. So we did like EDX, like more than 10 samples. So we didn't see any indication of any foreign atoms. And the company who Grove, they have the XRD with which again doesn't show any signature with the Raman. And so far all the TM we have done, we don't see any like foreign atoms basically in our crystals. So that's why we believe that it could be mostly from the defects, which is supported by the OLEX theory. And let me show you also the monolayer and bilayer, because so these are unpublished results, but I'm quite interested because observing that the magnetism in monolayer and bilayer would be also quite interesting, because this material system is a semiconductor, highly resistive, you will see. So this means that you can also use this as for proximity studies. So we spent quite a lot of time to get the monolayers and bilayers, basically. So you can see the AFMs on this. So we cannot really basically do the lateral transport to see these magnet transport measurements, because these delta R's are small compared to these like hundreds of mega ohm devices. So we carry out the measurements in a vertical structure. Basically, we use a graphene as a bottom electrode. We put the platinum cyanide monolayer or bilayer, and then we put the top contacts by, again, the non-magnetic material. And we try to do like vertical transport on this as a function of magnetic field. But before I show, so here you can already see that it's like less than 0.1 nanoamp of current with the application of bias of 2 volt at low temperature. So the material is like completely very resistive. For instance, like you can very reliably use this as a magnetic substrate for graphene or other TMDC materials. And yeah, from temperature dependence also showing the insulating behavior. And whenever we were looking these vertical devices, if it's made with the monolayer platinum cyanide, we were seeing kind of antiferromagnetic ground state ordering, and in the bilayer case, we see the ferromagnetic ground state ordering. So we don't have really like the full picture yet. So these are very, very recent results, but Oleg student, he was doing just some calculations. So let me tell you like very basically what's happening. So in the monolayer case, so these small circles, these are just like cartoons. We have also the data to just simplify. Basically, we have like bottom selenium, which are small holes, and then the top selenium atoms, which are bigger circles. So you can see that indeed, based on our calculations, it's like more stable to have like a spin down through the bottom selenium if you have the platinum vacancy, and spin up through the top. So it just shows that there is a antiferromagnetic behavior. And in the case of the bilayer, the calculations, it shows that indeed it's the interlayer interaction, it quenched the magnetic ordering for the bottom selenium atoms. So basically, they are magnetically dead. So everything is just coming from the spin up of through the top selenium atom, and therefore these first calculations that we have, like we just had the last Friday, so it suggests that there is a ferromagnetic ordering in bilayer. And let me just talk a little about the outlook, what you can do with these systems. So basically, like these, the vacancies that I was showing, indeed, these are like non-intentional defects. So whenever you grow these materials, you have the point defects, but the critical temperatures that we see is quite low for any applications. But indeed, you can improve it by engineering the samples. For instance, there are already like some calculations how the formation energy will change if you are doing the growth in the selenium-rich or platinum-rich environment, that you could have more control on the defect concentration. So I'm showing this slide because yesterday Oleg was replying to Yaro about this treatment. So we had like first attempts. Basically, we characterized one of our device, and we got the MR response. For instance, like we see the delta of 0.25 ohm, and the MR percentage is around 0.1. So we did like very short plasma treatment to create more defects. This is very uncontrollable compared to this growth method, that growth technique that I was just telling you. But what we could already see, like just like with the very short time of the plasma, indeed this delta R was increasing a lot. And for instance, like the MR value, it was going from 0.1 to almost, I think, 3-4%. And the critical temperature in this one was around 4.5 Kelvin. And in this one, I think it was almost 40 Kelvin. So this is not telling anything, but what it's suggesting is indeed like you can try to manipulate the defect concentration in this material more, and you can, in principle, increase the critical currents in this material system. And as Roland was mentioning, platinum cyanide is not alone. There is already a very nice study from the Columbia group, and they were showing that in molybdenum telluride, they have by the spin resonance measurements, they were showing the magnetic ordering in their crystals. And they also say that the origin could be the molybdenum vacancy or the anti-sighting effect. So I think most of these crystals, as long as you can create you can tailor the defect concentration or the type of the defects, then you can make these materials from non-magnetic into the magnetic. And they could be quite important because most of the intrinsic magnets that we have, they are quite unstable. So this could be expanding the range of the 2D magnets we have. And in summary, so this is the picture we have basically right now. We have like kind of like a layer dependent ordering. So we see that by changing the one layer, we go from the ferromagnet to anti-ferromagnet. I don't know if it's like true for all the thickness range. We of course couldn't measure like 40 devices. But so far, all the measurements we do, they suggest this. And whenever you go above 20 nanometer, the magnetism completely disappears. And this kind of magnetism, I also find it quite interesting because, for instance, Roland was showing this very nice summary curve from this review article. So all these 2D magnets have been like studied so far. Indeed, their parent compounds are also magnetic. And what's happening is like in these materials, once you go to monolar limit, what's happening, the critical temperature is just reducing. And but in the case of the platinum cyanide or this molybdenum telluride, we have a chance that we have like a non-magnetic in bulk, but once you go to 2D limit, then you start to realize the magnetism, which is showing the good property of having 2D materials. And also, since it's just like a one layer or few layer material, you can more easily control the defect types or the concentration. And I will put this silly slide. So if you look at this commentary in Nature Materials, so Rabi, he gave a comment, I think, about some people ask him like about studying the defects, and he called it like the Columbia Physics is not a place to study the physics of dirt. But indeed, if you look right now, by using this the dirt, you indeed can introduce magnetism, which is not normally in the pristine form. So with that, I would like to acknowledge my collaborators. So Andras Kiss, he's the head of the group, and he has been very helpful with this study. And the students, Charion and Alberto, they help with the device fabrication, and Mukesh is doing the TM. And the theory comes from Oleg and his brilliant PhD, Michele. So it's quite a joint effort. And that's all. And we have also, I have time, we have also one colloquium article we just put on archive. So maybe you can have a look, and you can also give feedback before it becomes online, so that we can make it more complete if we miss anything. So if you have any question,
We have time for one question.
I have one question. What I found is if you increase the radiation dose, you can create the defect, right? So I just wonder, in the absence of a defect, you just use radiation, can you introduce nanomagnetism?
Can I increase?
Yeah.
What?
So in the presence of defect, you use the radiation, you can change the density of defect.
Yes.
For the pristine materials, you just use radiation. Can you introduce nanomagnetism?
What we are sure is like we are introducing all type of the defect. We have the selenium and the platinum, maybe double platinum vacancies. So we are still doing the TM on these devices, and I also just say like it's not very controllable. But based on the first principle calculation that Oleg's group did, is like this selenium or double selenium or even double platinum, they don't induce any magnetism. So we believe that even though we create those additional defects, they're not really doing much. So the whole purpose is just like, this is very dirty way, but the whole purpose is just like create as much as we can do and see how it changes. I think if one really wants to investigate how the defect types or the concentration have impact on the magnetism, so simply the method should be just growth. So either you grow under selenium-rich environment or platinum-rich environment, and then you just modulate all these vacancies. So there have been already like some studies with the MOS or tungsten dicyanide, how people were trying to do. So the same approach can be also utilized here.
If I understand correctly, the explanation for the magnetism in your flakes is that you have some spin polarization in the top layer and the bottom layer, right?
Yes.
But do you have any clue how this would happen in exfoliated flakes?
These
Because
are
where, yeah, but then where would the defects appear? Because if you have defects throughout the whole crystal, then would you still expect magnetism to appear only in the top and bottom layer?
Yeah, I think so. So what we are sure is like there are still some vacancies in between the layers, but based on the this research is indeed like really like getting so much insight from the theory. So that's how we try to understand the results. So based on what they say is indeed like even if you have these vacancies in between the layers, which I'm sure we have many of them, and they don't contribute anything to magnetic ordering. That's what they say.
Unfortunately, we don't have more time now for further questions, but let's thank Ahmet for very interesting talk.
Thank you.